Hi, this is the Pumped Project. We are creating a device for the automatic weighing, labeling, and tracking of breast milk bags. We are sponsored by Victoria Rodriguez and Matthew Haberman. We're Group 15. These are our members: myself, Augustine Rodriguez, computer engineer; Jimmy Rawls, electrical engineer; Eric Hernandez, computer engineer; and Kevin Hernandez, electrical engineer. Our primary motivation for taking on the sponsored project of creating a device to automatically label and track breast milk bags was the fact that this device just does not exist. This is a device that can improve people's lives, but people just don't have the opportunity to use it. The reason it's helpful is because currently labeling bags is a manual process left in the hands of exhausted mothers. So our goal is ideally to make their lives easier.
For our basic goals and objectives, we are wanting for the device to accurately weigh the breast milk bag placed on the scale portion of the device. We want the device to print labels containing volume, date, name, and ID for each individual bag. We want an integrated app that displays current breast milk for stock for the user and ability to look up specific bags with ease using a designated ID. The device is portable and easily carried around, and the OLED screen displaying various bag information. For advanced goals and objectives, the app notifies the user that its breast milk bag is approaching its expiration date. Users can add detailed allergens information to each bag inside the app. User is able to print in three stages: offline, online, and offline while in sync. Battery charge will be displayed on their screen in real time and also showing changes when charging. For our stretch goal, the app shows detailed daily, weekly, monthly production stats. Individual users can schedule a drop-off time with local hospital milk banks and automatic shutdown device depending on certain conditions. The engineering specifications for our device and our project should be as follow. The weight should be accurate, which should be plus or minus 3 grams. The time to print after pressing the button should be 7 seconds or less. The time for recorded breast milk bag data to be sent to the mobile app should be 5 seconds or less. Time for breast milk bag to be weighed after placing on our load cell should be 3 seconds or less. The device should be 8 pounds or less for it to be portable. The battery voltage should be 12 volts or less. Battery capacity to be at least 10 hours, and the battery lifespan should be at least 2 years.
Choosing our microcontroller was a fairly straightforward decision. We did have previous experience using the MSP430, but since it has no wireless connectivity, it's not a good choice for this project. Since our device required Bluetooth capabilities, we immediately looked at the ESP32, specifically the room. It has all the connections we need for using our other peripherals and sensors, and it's fairly cheap. Additionally, its power usage is not overly significant. Due to its ease of use and large community support, we felt it was a fairly obvious choice. Finding the right printer was one of the most important parts of this project. We knew we wanted a thermal printer due to their compactness and reliability over time, since you don't have to refill with ink or laser cartridges. We also knew we wanted a printer that connected directly to our ESP32 via UART serial connection for data integrity and reliability. With those requirements in mind, we ultimately sought to find the printer with the lowest operating voltage that still maintained high print quality. We did find that with the MC206H embedded thermal printer.
When choosing our display, we had a few requirements that we needed to pass. One of them, we either had to have an I2C or an SPI display that would be capable of communicating with the ESP32S room. The voltage of the display needed to be between 3 and 5 volts, and we also needed an adequate size, not too big and not too small. The the one that we went with is the Hiletgo SSD 1309, which is an OLED display. The size of it is 2.42 inches. The resolution is 128 by 64. The voltage is capable of reaching if being between 3 to 5 volts for it to work, and there was two variations on Amazon, either for I2C or SPI, but we ended up going with the SPI interface communication one because we thought that it was the most reasonable one to go with.
For our power supply, we looked into a few different options, including AA rechargeable batteries, lithium ion cells like 18650s, and pre built USB power banks. Our goal was to find something that was safe, reliable, and that was capable of providing at least 2 amps of power to our thermal printer. The AA batteries were easy to find, but couldn't provide enough current, especially for our printer. The 18650s gave us more power, but it would have required us to design a custom protection and charging circuit, and it could have possibly added risk and complexity to our design. So in the end, we went with the USB power bank. It ended up being our best choice because it gave us a regulated 5-volt output. It has built-in safety features and provided us a simple way to power the system without the need of designing a custom battery circuit. After deciding to go with a USB power bank, we compared several options. This included the Talencel YB12, the Romos PHP30 Pro, also known as the Romos Sensei Plus, and the Romos PEA40. All three of these batteries met our minimum energy requirements of around 100 watt hours. The PEA40, however, offered the highest capacity at around 148 watt hours. The issue with this battery was that it was just too bulky for our design. The Talon cell, while it was compact, it was more expensive by about $20. So in the end, we went with the Romos Sensei Plus. This battery gave us the best overall balance of capacity, size, and price. It delivers 111 watt hours, has dual USB-A outputs, and it includes built-in protection against overcurrent, overcharge, and short circuits, making it a reliable choice for powering our system.
To power the various components in our device, other than the thermal printer, we needed to step down the voltage from our power bank to 3.3 volts. After comparing multiple voltage regulators, both linear and switching, we chose the LM2576 switching regulator. This decision was based on several key factors shown in the table. The LM2576 supports a wide range of input value or voltages, provides up to 3 amps of output current, and maintains high efficiency, critical for battery-powered designs like ours. Compared to the low-efficiency linear regulators like the AMS 1117, the LM2576 offers much better performance with significantly lower heat generation. It also includes protection features like over-temperature and over-current shutdown. Since our device uses Bluetooth Low Energy, or BLE, we were also mindful of the possible noise interference from the regulator's switching element. To minimize any noise from the regulator affecting wireless communication, we placed the MCU's antenna and the voltage regulator on opposite ends of the PCB. Overall, the LM2576 gave us the best balance of efficiency, current capacity, and noise control for our design. Weighing technology comparison and selection. When choosing a scale for our device, our main priorities were accuracy, reliability, and stability over time. We needed a solution that could quickly and consistently measure weight to help users keep track of their milk inventory with confidence. After comparing different weighing technologies, including capacitor load cells and piezoelectric sensors, we selected the strain gauge load cell. As shown in the table, the strain gauge load cell offers several key advantages. It provides sufficient accuracy for static weight measurements. It has plenty of resources for implementation into our design. It is very stable over time, which is important for inconsistent readings. And it is a low-cost part, perfect for our purpose. Capacitor and piezoelectric sensors were less favorable due to their higher costs, their moderate and poor stability, and their more complex signal processing requirements. In the end, we chose a 10 kilogram load cell, strain gauge load cell for simplicity and cost, making it the best fit for our application. ADC comparison and selection. When choosing an ADC to pair with our load cell, we focused on resolution, ease of integration, and cost. We evaluated 3 options: the ADS1256, the HX711, and the built-in ADC in the ESP32. In the end, the HX711 clearly stood out as the best fit for our device. The HX711 offers 24-bit resolution, which ensures high measurement accuracy. It requires very little programming and is designed specifically for load cells, making integration straightforward. It is also significantly more affordable than the other ADS1256 ADC. The ESP32's internal ADC, while convenient, only supports a 12-bit resolution and would not provide the level of accuracy we need for precise weight measurement. In the end, the HX711 gave us the best balance of performance, simplicity, and cost effectiveness for our load cell integration.
Here is our hardware block diagram. At the top, we show the battery feeding into our power switch, which then supplies power to a 3.3 volt regulator. That 3.3 volt output powers the ESP32 microcontroller and several key peripherals. This includes the OLED screen, the HX711 module with its load cell, and the user interface buttons. The thermal printer draws a lot of current, so we're powering it directly from the power bank's USB output. We also have a set of battery percentage sensors, which use photoresistors to detect the status LEDs on the power bank and report the battery level to the ESP32. At the center of it all is the ESP32, which manages all of our inputs and outputs, processing the weight, handling user inputs, sending data to the screen, and wirelessly communicating with a mobile app using Bluetooth. Power lines are shown in red, communication lines in blue, and wireless Bluetooth connections are represented by dashed black arrows.
This slide contains our 3.3 voltage regulator PCB schematic. We got this design from Texas Instruments LM2576 voltage regulator datasheet.
Here's a high-level overview of our pump device schematic. We broke it down into 5 key sections to keep everything modular and easy to follow. First, we'll cover power management, which includes our USB power inputs, on-off switching, and voltage regulation. Then we'll move into controls and logic, which spans 3 slides, starting with the ESP32 microcontroller, then the USB to UART circuit with its auto reset features, and finally our power status LEDs. We'll finish with the peripherals and expansion section, where we connect devices like the OLED display, printer, load cell, buttons, and additional I/O for future upgrades. Each of these sections play an important role in powering, controlling, or expanding the system, and we'll walk through how we brought them all together. For power, we designed the system to run off 2 USB-A inputs connected to the power bank. These inputs go through a power switch, giving us full control over turning the device on or off. One line powers a 3.3 volt regulator, which supplies most of the system's components. The other line powers the high current thermal printer directly. This section highlights our ESP32 microcontroller, which handles our communication, processing, and controls for all of our peripherals. We added boot and reset buttons with pull-up resistors to allow manual flashing and resetting whenever needed. And there's also a status LED on IO27, which is toggled by a transistor, which helps us confirm if our code is running correctly or not. This portion covers the CP2102 USB to UART chip. It's used for uploading code to the ESP32. It is powered through a USB 8 port and protected by a TVS diode on its data lines. We also added auto reset circuitry using 2 NPN transistors so that the ESP32 enters flash or reset mode automatically during programming. This section shows the 3 power status LEDs we added for quick visual feedback. The first LED is tied to the USB V-bus line, and it lights up when the programming port is active, which confirms to us that our MCU is receiving power during programming. The second LED monitors a 5-volt rail directly from the power bank, which powers the thermal printer. And finally, the third LED is tied to the 3.3 volt rail, confirming that our regulator is functioning properly and powering the rest of the system. In the peripherals section, we added several headers to keep our system modular and easy to expand. The OLED has its own SPI header, and we included 2 spare I/O headers, one of which we are actually using to connect to our battery level indicator PCB. There are also dedicated headers for OLED and printer power, printer communication, buttons, and the HX711 module. This slideshow shows the layout of our custom MCU PCB, which brings together all of the system's power, control, and peripheral connections. At the bottom, we have our 2 USB-A power inputs, and on the left-hand side is the USB-A port for programming the ESP32. To help reduce interference and ensure reliable uploads, we tried positioning the CP2102 circuitry as close to the programming port as we could. The ESP32's antenna is located at the top right of the board, and we cleared the ground plane beneath it on both the top and bottom layers of the PCB board to help with wireless performance. At the bottom right, we see some traces for our printer power lines. We made sure to make these 32 mil traces so that they can handle the higher current draw. And finally, we added mounting holes on the corners of the board so that we can safely secure it inside of our enclosure without it moving around.
We decided to go with the Romo Sense 8 Plus battery bank over regular batteries. This was a great opportunity for us to create a well-rounded portable device that had a capability of being rechargeable without any concerns. We did run into an issue on how the consumer was going to determine what the battery percentage was going to be, but we knew that the battery bank was capable of illustrating the battery percentage through the 4 LED lights. So, with the help of Dr. Weeks, we came up with an idea. Using photoresistors to determine the battery percentage based on the LEDs on the battery bank. The way photoresistors work is that the material has high resistance when in the dark and lower resistance when in the light. We're going to sync this up with the ESP32, and we're going to be able to determine the battery amount based on the amount of LEDs, which is 4, that are on and off. After speaking with Dr. Weeks, he gave us an idea to use photodiodes to measure the battery, but we didn't need to measure high light speed. That is when we came up with an idea to use 4 photoresistors, one for each LED. They will be directly attached on top of the battery bank via a compartment. It would then be connected to the MCU via an ADC connection, and then the MCU would transmit it onto the display. The images in front of you are the 3D view diagrams of the PCBs that we have created. On the top left, we have the voltage regulator. Under that, we have the battery indicator. And on the right side, we have the main PCB board for the MCU.
Here we have the 3D printed enclosure for our device. It's a multi-part design made so that each part can be printed flat on a 3D print bed, which makes it easier to print. The overall dimensions of the enclosure is 8 by 6.5 by 5.25 inches. At the top, we have our weight plate. This weight plate is actually sealed with a couple of O-rings beneath the screws. This helps prevent any liquid from actually going down into our enclosure. Beneath that, we have our load cell base. The load cell is actually raised off of its bottom by about 3 millimeters so that it can actually bend and measure. The top of the load cell is then connected to the weight plate with an extender. This allows the weight plate to directly apply the weight onto the sensor. We also added threaded inserts and counterboard holes to each printed section. This allows us to securely assemble the enclosure while also allowing us to disassemble it without worrying about the threads from breaking. On the back of the enclosure, there is a magnetic hatch that we can take off so that we have access to the ESP32 for programming. This allows us to program our device without having to take apart the enclosure. And on the left-hand side, we have a little mount for a USB-C cable along with a little cutout so that the user can recharge the battery bank without having to take apart the enclosure. So this is our battery indicator mount. This small 3D printed mount was designed to read the battery level from our battery bank using its pre-built-in LED indicators. The mount holds 4 photoresistors, all angled at 45 degrees. This angled layout was necessary because the photoresistors were just too wide to actually sit next to each other above each LED. The wider base part of the design was added so that we can actually secure the mount to the battery bank using glue and tape. And yeah, this mount just gave us a safe, non-invasive workaround for actually monitoring the battery levels of our battery bank.
Our breadboard prototypes so far have been very successful. We've hooked up all our major components and printed labels while simultaneously sending data over a BLE connection to an Android. Additionally, we have also tested a sort of fuel gauge for our power bank using photoresistors.
Prototype troubleshooting. We encountered two major issues during prototyping, both related to the thermal printer. The first issue was with our original printer. It was rated for 5 to 20 volts, but in testing it only printed clearly at 17 volts or higher. Since our power bank maxed out at 12 volts, we decided to replace the thermal printer for a new one rated for 5 to 9 volts at 2 amps, which worked well with our existing setup. The second issue came up when we were using a 5-volt LM2576 voltage regulator to step down the battery output to 5 volts for the thermal printer. However, due to limitations on the power bank's output port, the regulator output dropped to about 4.3 volts, resulting in blurry prints. We solved this by removing the regulator and connecting the printer directly to the battery, which restored print clarity.
As previously mentioned, this project has an associated mobile application to utilize the device. We are building it specifically only for Android due to time constraints of the summer semester. We are using Android Studio and building most of the app's UI using Kotlin and Jetpack Compose. For the backend, we are connecting our app with a Firebase real-time database to store info. As previously mentioned, this app will be connecting to the ESP32 via BILI connection and sending plus receiving data via this connection. Hi, this is our overall software block diagram. It all begins when the ESP32 turns on and begins to advertise its BLE connection. When this happens, the scale initializes and starts to display its readings. When the user presses the print button, the current reading is frozen on the screen. And then we check if the user is offline or online. If the user is offline, we only print the offline label. It has limited information about the bag. If the user is online, it meant the Android app connected to the ESP32 and sent the user info to it via BLE. The online label contains complete information not only about the bag, but also what the user it belongs to. For the online print, we write the bag to the app via BLE as we print, and from there the app takes it and displays the bag in its virtual inventory, and simultaneously it also writes the bag to the database via the internet. From there, the user has the ability to manage their inventory by searching it and deleting used bags.
Here we have the mobile app diagram. When the user opens the app, the person is going to be prompted either to log in or to sign up. If they choose to sign up, then they're going to go ahead and enter their credentials, which then after clicking confirm, they're going to be prompted to do an email verification. After doing their email verification, they're going to be sent straight directly to the login page. When logging into the page, they're going to go ahead and enter their credentials and be sent to the home page. In the home page, there are a few features there. There is a logout button, there is a BLE device connection indicator button, settings, and milk storage inventory. In the logout page, they're going to be able to go ahead and log out and then return to the login sign up page. Settings is going to have some information where they're able to change their personal information, delete the account, and disconnect/reconnect the new device. In the milk storage inventory page, they're able to see their inventory, edit the inventory, add and remove specific information, and be able to reprint the specific label. When choosing the front-end framework, we decided to go with Jetpack Compose. It is not cross-platform. It uses the language Kotlin, which is similar to Java in the sense of it uses classes and functions. It is a function-based UI. It is built in live preview and live updates. It is growing. It has a lot of modern features, and it is used. You can use it in Android Studios, and it's really good. It has tight integration with modern Android APIs, such as Firebase, and it is positioned by Google as a feature of Android UI development. The reason why we went with a non-cross-platform framework is because we wanted to solely focus on Android and not iOS. The reason for that is because we have previously ran into issues with connections and development using a cross-platform framework. We also wanted to get the best features that Android Studios and Jetpack Compose has to offer.
Our backend selection was heavily motivated by the fact that we were making an Android application. Firebase is a backend as a service owned and maintained by Google, who also created and own Android. Because of this, there's a natural synergy where Android applications built in Android Studio, which is the IDE we're using, have heavy built-in support, and as a result, access to a lot of really powerful tools that make our life easier. Additionally, Firebase has a real-time database that will ensure minimum latency for our Android device when it comes to updating the app in real time. Another reason we chose Firebase is that this is a sponsored project that our sponsors have expressed interest in possibly commercializing. With that in mind, Firebase was an obvious choice as it has a generous cost plan that allows free usage for small products and very fair rates for products that are significant marketplace competitors.
Here we have 4 images. Each image illustrates us testing our PCBs. In the bottom we have all of our parts separated outside of our 3D enclosure. They are being tested with our computer. And on the top left we have our battery indicator PCB. We are testing outside with our ESP32, making sure that we are getting the right measurements for our brightness indication. In the middle we have all of our wiring for our main PCB inside of our enclosure, and on the right side image we have most of our PCBs inside of our enclosure. Here we have our expenses broken down. We were given a budget of $500, but in reality we ended up spending $578.06. The reason why we went a little bit over the $500 budget is because we had to test run a few printers, about 2 to 3 or so, and also we had to do 2 separate orders of PCBs. In this table we have the items, the cost of each item, and who purchased what item from within the group.
This slide contains our work distribution breakdown, showing group member assignments and secondary personnel assigned to those assignments.
We were given the schedule of Senior Design 1 and Senior Design 2 combined. In the top, we have the Senior Design 1 schedule. We have it broken down from the beginning of group formation, from week 1 all the way to the last week, which is the break before the summer term. A lot of the events are basically going on against one after another, but there are some that are overlapping because we are working simultaneously in different tasks. Down in the bottom, we have Senior Design 2 schedule, where we are currently working on right now, but it also starts off from right after the break schedule that we have for the summer break. And then we have it set up for the beginning first week, which is the EBIT lecture 1, all the way to the end of basically Senior Design, which is the final presentation. We didn't see much of a shift in our schedule, and we actually worked ahead of time, so that is a benefit to us. And yeah.